The atmosphere has a composition. The atmosphere has a structure, and it also has circulation. One of the main components of atmospheric circulation are what we call Hadley cells. Now, the fundamental cause of atmospheric circulation is the uneven solar heating of the Earth's surface. Here's figure 2.6, which demonstrates this pattern that the Earth is tilted on its axis. So at any one point in time, the equator is receiving more direct rays than any of the polar areas. The arrows parallel to the sun's rays show the depth of the atmosphere that the solar radiation must penetrate. And in the tropics, it's relatively low, and in the polar regions, it's relatively high. It just has to pass through a lot more of the atmosphere. And as a consequence, polar regions, in addition to receiving less solar radiation per unit area because of the tilt, there's also a greater chance that that shortwave radiation is going to get reflected in one fashion or another. So high latitude ecosystems receive less radiation than those at the equator because radiation at high latitudes has a longer path through the atmosphere and it's spread over a larger ground area. The sun's rays have a longer path through the atmosphere at high latitudes, and more of that incoming solar radiation is either absorbed, reflected, or scattered before it reaches the surface. That's one of the main reasons that we have uneven heating across the Earth. Now, to demonstrate this, this is actually the net flux of energy at the surface of the Earth at different times of year. So this is the solstice in December, here's the June, and then here are the equinoxes. So equinoxes, things should be relatively even, and you can see that most of the heating during the equinox is centered at the equator. And by the time we look at the winter, for northern hemisphere winter, you can see that a lot of that energy is shifted to the southern hemisphere, and during the northern hemisphere summer, a lot of it is shifted now to the northern hemisphere. So this shifts back and forth during the season, but on average it's always highest at the equator. The reason that we have circulation within the atmosphere is that energy is transferred poleward. This here is a net radiation budget, and the x-axis for the top panel is radiation, and this amount of energy that's absorbed. Happens to be petawatts per degree. And then here's latitude. So you can see for radiation gain right there at the equator, it's highest. But if you take a look, that there's a gap, that there's a lot less radiation that's lost at the equator than is gained. But by the time you look at high latitudes, for example, you can see that there's a lot more radiation that's lost from these latitudes than is gained. And that's due to the shifting of all this energy that's gained at the equator to higher latitudes. Now there's two main vectors for that energy to reach high latitudes. One of them is the oceans and the other is the atmosphere. And you can see the amount of energy that's transported by the oceans versus the atmospheres. By and large, it's the atmosphere that transports a lot more energy than the oceans do. So how is so much energy transferred by the atmosphere to higher latitudes from the tropics? Well, that's atmospheric circulation. The thing to know about atmospheric circulation is that it has both vertical and horizontal components. We talked about how air that was heated up rose, and now we're going to kind of understand why air also moves horizontally. So the vertical energy transfer that happens above terrestrial ecosystems is part of the reason why air is going to flow horizontally. So surface heating causes air that's at the surface to expand and become less dense. So if this is the surface of the Earth, it heats up right here, it's going to expand, and as a consequence, it's going to rise. Now in the tropics, for example, there's going to be a lot of air that rises. It's going to be heated up a lot, and just over large, vast areas, a lot of air is rising. as that air rises, cooling causes condensation and precipitation, and so we're going to get clouds that form. But this condensation of water actually releases energy, and that causes the air around it to warm up and rise often even more. Now, this vertical pattern of temperature is called the lapse rate, and it varies regionally. On average, though, it's about 6.5 degrees Celsius per kilometer within the troposphere. Now, what's important to know about that vertical movement is that that's what generates horizontal movement. So if this is the surface of the Earth, we talked about how in relatively hot places there's a lot of vertical movement of air above the surface of the Earth. And as that air rises, the pressure here decreases a little bit. You've got a rising of the air. And consequently, air has to flow in from the sides to fill this void. And that sets up a circulation pattern. So this air rises, air moves in, it creates a void behind it, and then this air that had risen up flows over to the side and then eventually down. And this is a cell that's driven by rising air. Now, these cells exist on a global scale, and the ones that are closest to the equator are called Hadley cells because of all of the energy that is absorbed in the tropics and how hot it gets. There's a lot of rising air on the equatorial region. And as that air rises, it's then air from higher latitudes, both north and south, come in to fill that void, and you have this large movement of the atmosphere, circulation, to fill that void. It eventually descends and then comes back and cycles through. And that is called a Hadley cell. So, to recap, tropical air rises, and it rises almost to the top of the tropopause in many places. There's a lot of heat that's released by condensation of water, and that upward movement and expansion of equatorial air creates a horizontal pressure gradient that causes the equatorial air to flow horizontally. So tropical air rises, it cools, it releases heat, and that horizontal pressure gradient is generated. As that air moves poleward, it emits long-wave radiation to space. It's going to release heat, it's going to release radiation. And then it mixes with other colder air and becomes compressed into a smaller volume. And as a consequence, it starts to descend. And when it descends as high pressure. So all the heating that happens here generates an area of low pressure. That air cycles into more equatorial areas, releases a lot of energy as it goes, becomes compressed, and then sinks. And then eventually it moves back to the equator. Now, we've just covered a Hadley cell and what generates Hadley cells, but there are other cells too. So in this figure you see the Hadley cell here that originates at the tropics and flows down here, and there's other cells too, Ferrel cells and polar cells, that are other large-scale atmospheric circulation cells that occur, both transporting energy towards and away from the poles. Now, it's important to realize that when we think about climate and climate as a state factor, where does that climate come from? Why is it warm? Why is it cold in a particular place? A lot of that has to do with atmospheric circulation. And a large part of the climate in any one place is driven by circulation. The temperatures of a given area might be warmer or colder depending on the atmospheric circulation and how much heat is being driven towards or away from a particular area.